morning, everyone. Things look good on monitor 1. I'm gonna do my my usual chit chat while I wait for it to show up on my streaming services and make sure everything's going well. Oh my god. I've started monitoring Twitch and it just screamed at me about Nerf guns and that was very surprising. That was much louder than I thought it was going to be. And it looks like both services are working well. Excellent. Welcome, everybody. This is the third hour we are spending on this neural language models chapter. And actually, we're kind of close to done. So I know that we actually already read some of this, but I'm going to go through it again real quick today. And then I think we ended up with figure 7.12. The John 56789 says, let's go. Let's go indeed. So we looked at this this neural network graph, and I think we got to the section that referred to it. So here in pre-training. But then after that, there's honestly not that much more of the chapter. We're going to look at one more architecture, and then there's some discussion of training that's not very big, and then we have a final summary, and then some biographical and historical notes, and then it's references. So I promised on Twitter, if you follow me on Twitter, that if we finish this chapter, we might take a crack at some implementation possibly. So we might take a crack at some implementation possibly and spend some time actually building a neural language model. The previous two chapters, we learned about the structure of a neural network, how they work, and then we learned about training and backpropagation and the chain rule. And last time we got a little bit into language-specific stuff. So we started with this chapter, this part of the chapter, and we also talked about embeddings, which are a lower dimensional representation of a co-occurrence matrix. So basically you take a co-occurrence matrix for every word in your vocabulary, and then you project it down into a smaller dimensional space so it's more compact and portable. 500 and 300 are fairly normal, smallish embedding sizes. Sorry, coffee. I'm going to try not to slurp too much on the mic, but I do need the coffee. I'm very tired today. And the reason that we want to use embeddings in our neural language model is because actually meaning is important and words mean things. I don't want to get too much into semantics. Bubble Ride says, hello. Hello, Bubble Ride. But we do want to incorporate some way of representing meaning into our models, and that's what embeddings are doing for us. And I was also looking at what's it called? The analysis, the statistics, the information about who's watching the videos recently. And I did notice that there were a lot of folks on mobile. So I'm going to try to do a better job of making sure that my screen is very large so you can read it. Plus it's just, good accessibility. Okay. So let's pick up with this section here. So this is in 7.5.1. Let's see how this embeddings works in practice. Let's assume we have an embedding dictionary E that gives us, for each word in our vocabulary V, why is the dictionary called E? It should be called D. The embedding for that word, perhaps pre-computed by an algorithm like Word2Vec from chapter 6. And generally here, if you're working with a language that has them, you'd use pre-trained embeddings. Fingerful and Fab1 say hi. Hi guys, welcome. Figure 7.12 shows a sketch of the simple feed-forward neural network language model with n equals 3. We have a moving window at time t with an embedding vector representing each of the 3 previous words, words t-1, t-2, and t-3. These 3 vectors are concatenated together to produce X, the input layer of a neural network whose output is a softmax with a probability distribution over words. Bubble Ride says, my NLP skills are -1 out of 10. I don't think that's true. That's because you speak a language, so you have, well, I shouldn't say speak, you know at least one language, and that means that you have some knowledge of how language is put together, even if it's only sort of instinctual. So I don't think anyone starts at NLP at 0. If nothing else, you can like evaluate output and look at it and be like, yeah, it looks good, yeah, it looks bad. Whereas if I have like a, I don't know, machine parts labeling algorithm, if I don't know a lot about machine parts, I can't necessarily evaluate the output that good. So for NLP on your language, I think most people start beyond 0. But this is mostly network architecture right now. All right, hopping back into it. Let's finish this paragraph and then pop down and then look at the figure and talk through that. So we've got 3 vectors, they're concatenated together. And we take the softmax, which is a probability distribution over words. And these are the words that we have represented in our vocabulary V. Thus, y sub 42, the value of output node 42, is the probability of the next word, wt, being v42, the vocabulary word with an index of 42, which might be like, I don't know, lizard or whatever. Rich says coffee and donut. Kanishka says, do you have any idea why Kaggle prefers YouTube over Twitch? And Roshan says, hi. Kanishka, I am actually using both. I'm streaming to my Twitch and then also the Kaggle YouTube. I don't know. The account was actually set up before I joined, so you'd have to ask the marketing team. One reason that I prefer YouTube for streaming personally is that it saves the videos pretty much forever. And in Twitch, they go away after 2 weeks, I think, so you'd only have 4 streams at any given time. Okay. So this is sort of telling us in words what this architecture is doing, and we can pop down and take a look at it. Kanishka says, with Restream? Indeed, with Restream. Restream is the program that I'm using to stream to both Twitch and YouTube simultaneously. Okay, so here is a visual representation of the architecture we were just talking about. So we are looking at this word, and we have the previous 3 words as input. Fab says, tea and kitty. Aw, that's nice. I was snuggling with my hedgehog earlier, but I had to put him away. Kanishka says, oh, I see. I hate that YouTube has my name when I chat, lol. And Bubble Riot says, on Twitch, hello, so weird to listen to both Twitch and YouTube. I would probably mute one. That sounds awful. Yeah, I don't know if there's a way to change your name on YouTube. Sorry about that. Okay, so what our language model is doing is we have this string of input words, and we are sliding over it 3 words at a time and then predicting the 4th word. So this is our target word, and then here are the previous 3. And this is fully connected. So we're taking the embedding, which is pre-trained, for the, ground, and there. And they are words 35, 9925, and 45180 in our embedding matrix. Sorry, not metrics. Our embedding matrix proportioned over them. Oh God, what's the word? Anyway, this one goes with this one, this one goes with this one, and this one goes with this one. And that is used as our input layer, these embeddings for each of these words. As it looks like a single very long matrix, so a vector. And then we have our weights, and then our hidden layer, which has 4 nodes. And then our output layer, which has 1 node for every word in our vocabulary. And then we take the softmax over that, so the most probable word given the probabilities we've assigned to each word in our vocabulary. Rashik says, lol. I'm not sure at what point you said that. And Kanish says, looks like Bengio's an NLM. I am not familiar with that, so let's take a look. I'd say it's a fairly standard architecture at this point. It's in JMLR, which is a very fancy journal. Montreal, good school. Montreal is investing a lot into sign language. Fab1 says, I'm not sure if you can do anything about it, but the mouse is a bit small. I don't think I can. I will try and make it bigger in the future. I think I'm gonna have to change the resolution of my computer to do that, and I don't want to futz around with that on the stream. But thank you, good feedback. Show me the diagram. Okay. Yes, very similar, except it looks like there is, so in addition to feeding forward into the hidden layers, it's also directly passed to the softmax layer, and I don't know if that is to make it more probable that you're going to repeat words. Actually, it's probably to make it less probable that you're going to repeat words, so this is probably some sort of like little bump down if you have the same word more than once. I don't know. This is the second paper that I would need to spend time reading. Yeah, thank you. I was not familiar with that paper. I don't really read JLMR. I should start. But it tends to be less applications focused, and I'm generally more excited about applications. Bengio's vectors were probabilistic terms, I think. Yeah, it makes sense. So this is sort of the very basic architecture that you're going to see in a lot of places. Basic. We did a lot of heavy lifting to get here conceptually, but this is sort of, it doesn't have a lot of bells and whistles. The model shown in figure 7.12 is quite sufficient. Oh, it's good to know. Assuming we learn the embedding separately by a method like the word-to-vec methods of chapter 6. The method of using another algorithm to learn the embedding representations we use for input words is called pre-training. If those pre-trained embeddings are sufficient for your purposes, then this is all you need. Fab1 says, oh, the mouse size. You pointed to some points on a graph and I couldn't follow. Yeah, sorry about that. I will work on that. Oh, Bubble Ride is saying 42 is the word. Yes, it's a little, it's a reference to the Hitchhiker's Guide to the Galaxy. However, often we'd like to learn the embedding simultaneously with training the network. This is true whenever we have a task that the network is designed for. This is true when whatever task the network is designed for, sentiment classification or translation or parsing, places strong constraints on what makes a good representation. Let's therefore show an architecture that allows the embedding to be learned. To do this, we'll add an extra layer to the network and propagate the error all the way back to the embedding vectors, starting with embeddings with random values and slowly moving toward sensible representations. So this is going to take much longer to train because you have a bigger space to explore, basically. But if you are using a language for which pre-trained embeddings are not available, for example, that's pretty much your choice that you have. And then you can save out the embeddings that you've trained and use them other places. Although depending on what task you're doing, they may or may not be actually useful. Sorry, more coffee. Let's therefore show an architecture that allows the embeddings to be learned. To do this, we'll add an extra layer to the network and propagate the error, blah, blah, blah. Oh, we already said that. For this to work at the input layer, instead of pre-trained embeddings, we're going to represent each of the n previous words as a one-hot vector of length v. So we have as many spaces in the vector as we have words in our vocabulary. So if you have a bigger vocabulary, you're going to have a bigger space to train, i.e. with one dimension for each word in the vocabulary. I should finish sentences before rephrasing them. A one-hot vector is a vector that has one element equal to 1 in the dimension corresponding to that word's index in the vocabulary, while all the other elements are set to 0. Thus, in a one-hot representation for the word toothpaste, supposing it happens to have index 5 in the vocabulary, x sub 5 is 1, And for all of the indexes other than 5, it's 0. So we can see here there's a vector of length v for each word in our vocabulary, and we have turned the fifth term, the fifth item is 1, and all of the other items are 0. So it's sort of a... I'm trying to come up with like a good intuition metaphor for this, and I'm not coming up with anything. I think one-hot vectors are fairly straightforward, but yeah, so that you also somewhere have a list of what word is occurring at each vector. So figure 7.13 shows the additional layers needed to learn the embedding during LM training. Language model is LM. Here, n equals 3 content words. Here, the n equals 3 content words are represented as 3 one-hot vectors, fully connected to the embedding layer via 3 instantiations of the E embedding matrix. Note that we don't want to learn separate weight matrices for mapping each of the 3 previous words to the projection layer. We want one single embedding dictionary E that's shared among these 3. That's because, over time, many different words will appear as WT-2 or WT-1, and we like to just represent each word with one vector, whatever context position it appears in. Fab1 says, kind of like a dummy variable? Yeah, if you've ever sort of created categorical variables and turned them into numeric, that's the way folks do it. But much bigger, because you have presumably more than like 4 words in your vocabulary. The embedding weight matrix E thus has a row for each word, each a vector of d dimensions, and hence has a dimensionality of v times d. So basically, so in this situation, we are pulling out one row from an existing matrix, and the matrix is our embeddings for our entire vocabulary given our entire training set. So it's a big matrix of whatever the dimensions are for your specific embeddings, and then by v. So one row for each vocabulary item, and then we sort of peel out the rows that we want and then stick them into our model like stickers. But here we need to make the whole sheet of stickers. I don't know where the stickers came from. Here we want to make the whole sheet of stickers, and that is the embedding weight matrix E. So let's do the walkthrough and then look at the figure, I think. So step 1 is select 3 embeddings from E. So this is our embedding matrix that we're training. This is our sticker sheet, and we're going to peel off 3 stickers. Given the 3 previous words, we look up their indices, create 3 one-hot vectors, and then multiply each by the embedding matrix E. Consider WT-3. The one-hot vector for the is index 35, is multiplied by the embedding matrix E. That sentence doesn't make sense. So we have a one-hot vector for the, so we're taking the input for index 35 and we're multiplying it by the embedding matrix to give the first part of the first hidden layer called the projection layer. Since each row of the input matrix E is just an embedding for a word, and the input is a one-hot column vector x sub I for word V sub I, the projection layer for input W will be E of x sub I equals E sub I, the embeddings for word I. Okay, halfway through there, my brain just turned off. Ooh, sorry, winged my elbow. Let's go through that a little bit more slowly and see if I can understand words from it. So we have each row from our input matrix E is an embedding for a word, okay? And the input is a one-hot column vector I for the word. A projection layer for okay, I see. So we're using the one-hot vector to select the row from the matrix that we want, because we know the relationship between the index and the vocabulary and which word it is. So it's like we're looking up the address of the specific word that we're interested in. Okay, that makes sense now. 2 multiply by W, the weights. We now multiply by the weights and add the bias. and pass through the rectified linear or other activation function to get the hidden layer H. So this is sort of the very core standard process of moving forward through a neural network. Then we multiply by U. What is U? Where did U come from? Is this the softmax? U might be the softmax. Apply softmax. Okay, nope, U is not the softmax. Where did U come from? The letter U, not y'all. Y'all are great. Where did U come from? Blah, 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 blah. Oh, it's just a separate weight matrix. Okay. So it's another weight matrix that we are training and is being updated. Okay, that makes sense. And then we take the softmax of that. Okay. After the softmax, each node I in the output layer estimates the probability P of WT equals I given WT sub 1, WT sub 2, T sub W sub T minus 1, W sub T minus 2, W sub T minus 3. So you look at the previous 3 words, and for each word in your vocabulary, you predict the probability that the next word will be that word. So if I said something like, we ate all the cake would have a high probability, but we ate all the we, like WE, like the pronoun, would have a very low probability because that's not how English works. In summary, if we use E to represent the projection layer, formed by concatenating the 3 embeddings for the 3 context vectors, the equations for a neural language model become little e. So this is the projection layer, which is made up of the embeddings for each word in the vocabulary. H is sigma WE plus B. What's H? Oh, so this is the hidden layers. So the hidden layers are weights times the inputs plus the bias, summed over those. Z is the second weight matrix, and Z is the, what is Z? I thought I knew what Z was, but I don't think I do. So Z is the final layer before the output, and it's the hidden layers times this new weight matrix. And then we take the softmax of Z. So we just pick the most likely word. All right, now let's look at it in pictures. I know we're going over the same thing a lot, but this is fairly complex. And it's a, it's a foundational idea. Like if you go to an NLP talk about language modeling, they're probably going to assume that you've come in with this knowledge already. Okay, so we have our language input. So this looks fairly similar to the one we were looking at earlier. So the only things that are different are from the hidden layer down. So the hidden layer and then this weight matrix and then softmax over the output, those are all the same. So we are so we're taking a 1 hot vector for each of our words. We're using that to filter the embedding vectors, embedding matrix that we're also training. And we're using the same embedding matrix for each word. We're just filtering it by the row that the word is on. And then we're using that gives us our embeddings for each of our words. We pass that, multiplying it by weight, adding our bias term, applying our activation function to the hidden layer. And then we repeat the whole process with a different weight matrix. So we're not using the same matrix here and here. And this is learned, this is learned, and this is learned. I don't think the bias is generally learned. I think that's usually a hyperparameter you set. And then once we take those hidden layers and apply the second weight matrix, then we get our softmax output. And that's probably going to be wrong. So we'll propagate back through using backpropagation and update both of these weight matrices and the embedding matrix we're using. Mahima says, what is the session about? Neural language modeling. Fav1 says, is there a specific reason why we have 2 different weight matrices, W and U? I don't know. Usually you have Okay, so there's a practical reason, but I don't know if you can do transfer learning between layers. The practical reason is that this weight matrix takes as its input this single long vector that is times the dimension of our embedding times 3, and then passes that into our hidden layers, which are going to be, that's a parameter we set, the number of hidden layers. And this weight matrix takes in the hidden layers and converts it to the output layers, which is the size of our vocabulary. So the sizes are different. Kanishka says, U is to convert the input to the vocab length. Yeah. Yeah, so I think they have to be different because the inputs and outputs are different. So the dimensions are different. Oh yeah, that's what this is saying. So this is the dimensions of our hidden layer times 3 times the dimensions of our embedding, and then this is the vocabulary times the dimensions of our hidden layer. Excellent question, Fab One. But I guess there's, like, you can think of a possibility where you just sort of, like, have the same number of hidden layers as input nodes, and then that's also the size of your vocabulary, I guess, if you did, like, some finagling. Bubble Ride said, what is a 4-gram? So an n-gram, like the letter n/gram, is a representation of language that takes the set of all n words that occur together. So a 4-gram for, like, this sentence would be these 4 words, in summary if we, and then these 4 words, summary if we use, and then these 4 words if we use e, and it's that sort of, like, sliding thing. Kanishka says 4 words together like a bigram is 2 words together. Yep. Yeah, all right. I think I've cracked this. I think this is pretty good in my head. I think I understand what's going on here. We'll find out when we get to implementation, because I think we're pretty much done. All right, 7.5.2, training the neural language model. Fab One says, I butchered that word. Concatenated? Meh. I'm picking up what you're putting down. I'm also dyslexic, which you may or may not know about me, so spelling is, optional. There's a lot of variety in language. We can embrace the difference. Okay, to train the model, i.e. to set all the parameters, bias is trained. Okay, interesting. Theta equals E, which is our embedding layer, W, which is the weights from the embedding layer to the hidden layer, U, which is the weights from the hidden layer to the vocabulary, and B, which is the bias. B is usually bias. I don't see it in here. Okay. We do gradient descent using error back propagation on the computation graph to compute the gradient. And we talked about those last week. Kishna says, the beauty of language is that humans can still understand what you mean even if you typoed it. True. Humans are great. Training thus not only sets the weights W and U of the network, but also, as we're predicting the upcoming words, we're learning the embeddings E for each word that best predict upcoming words. So something about this, Ryan says, B was the bias inside the activation for the hidden layer. Hidden layer. Oh, I see it. Okay. Thank you, Ryan. That was helpful. And now I've lost where I was. We're learning the embeddings E for each word that best predict upcoming words. Little side note about embeddings, especially if you're training them in this way, they're gonna probably be fairly brittle. Hredix says, where can I find parts 1 and 2? They should be on the Kaggle channel under the Kaggle Reading Group playlist, which I'm fairly sure I updated correctly, if you wanna follow along. So if you're training embeddings on a specific, like, genre of text, like tweets, they may not necessarily, like, transfer well to classic literature because people tend to use different types of words together. So genre effects are important. Generally, training proceeds by taking as input a very long text, concatenating all the sentences, starting with random weights, and then iteratively moving through the text, predicting each word WT. So instead of looking at each sentence individually, we create a single long text that is made up of all of the sentences as a single string. At each word WT, the cross entropy, negative log likelihood loss is L equals negative log P of P, the probability of WT given WT minus 1, etc., etc. So you look at the previous words, you have the probability of the current word, and then you take the negative log of that. The gradient for the loss is then theta t minus 1 equals theta sub t minus nu, maybe? Like a little lopsided n? I think that's new. I'm going to decide it's new. And this guy, which last time we decided to call D, so I'm just calling it D, D minus the log probability of WT given WT minus 1, etc., all the way back through, divided by D theta. Several people have said that that is eta, so that's eta. So that's not a new. This one's an eta. Yeah. This gradient can be computed in any standard neural network framework, which will then back propagate through W, U, B, and E. Training the parameters to minimize loss will result both in an algorithm for language modeling, a word predictor, but also a new set of embeddings E that can be used as word representations for other tasks. Maybe. Bubble Ride says, are those embeddings, do the embeddings consider typos like automobile, A-U-T-O-O-M-B-I-L versus automobile, A-U-T-O-M-O-B-I-L-E? They will not by default. So one thing that you could do to get around that is you could do some pre-processing where you use fuzzy matching to sort of cluster things together that you think are likely to actually be the same word. Yeah, but then, there's information in a typo, right? There's probably genre information. I'm much less likely to make a typo in blog posts that I'm publishing than I am on just sort of, text I'm sending to my friends. Usually you'd probably assign UNK or unknown token to those because they're probably going to be out of vocabulary unless there's a whole bunch of them. Ryan Coatney says something like edit length. Yeah, that's generally fuzzy matching is based on edit length, or edit distance, rather. So the number of characters you'd need to change in order to take input A and turn it into output B. I don't know why I gave those letters. They don't need letters. Yeah, and actually there's a really good discussion about this on the Quora competition forums right now, because there's a lot of typos and people are like, well, what do we do with them? Yeah. It's a challenge. There's several approaches you can take. Chirag says, how does n-grams actually work? Can I create a specific logic being centric to a special domain of knowledge? Yes, n-grams are also going to be fairly text specific or domain specific. The thing is so embeddings like this include a language model that's trained on embeddings include information on sort of meaning and sense, kind of. So like the idea that cat and dog are more alike is going to be captured by this neural language model, and it won't be captured by n-grams. N-grams just look at what happens next to each other. So yeah, n-grams work well. They're much cheaper to train. If you have a small vocabulary, they tend to be a little bit less effective because you have fewer instances of things together. Yeah. Trog says, say in medical terms. Yeah, no, absolutely. You could use n-grams in medical terms. If there's going to be a lot of repetition in your data set, n-grams might be more useful. Yep. Yeah. Training the parameters to minimize loss will result, we said that. So you get out a set of embeddings and also task specific model. Summary. Neural networks are built out of neural units, originally inspired by human neurons, but now simple and abstract computational device. That's probably supposed to be simply, but now simply an abstract computational device. Each neural unit multiplies input values by a weight vector, adds a bias, and then applies a nonlinear activation function like sigmoid, tan, or rectified linear. now, to the best of my knowledge, most people use ReLU or leaky ReLU, except in the final layer, and there people tend to use sigmoid. I haven't seen a lot of work with TAN relatively recently. Trog says, what about doc to vec or dependency to vec? Will it be better? I mean, I don't know about your particular application. That's an empirical question. You should try it out. In general, I tend to be a little bit leery of embedding things much larger than phrases. So my background is in linguistics, and I believe in syntax and constituency structure and embeddings for. Sorry, this is getting more into stuff than I necessarily want to get into. But if you're trying to capture things like the relationships between words in a sentence, I don't think embeddings is the best way to do that. I think that at that point you would do parsing. Subham says, what is softmax? Softmax is when you take the output of you have a bunch of probabilities, and you're like, take the thing that's most probable. Bubble Ride says, so training means fitting W sub t to f of W sub t minus 1, etc. Yeah, so during training, we will look at these 3 words, predict the next word. If we're right, we get a little reward. If we're wrong, we get a little sort of, I don't want to say punish, but we sort of back down from that area of exploration, and then we sort of bump over, and then we try the next word, etc., etc. In a fully connected feed-forward network, each unit in layer I is connected to each layer in I+1, and there are no cycles. So we are not looking at recurrent networks here. The power of neural networks comes from the ability of early layers to learn representations that can be utilized by layered layers in the network. Neural networks are trained by optimization algorithms like gradient descent. Error backpropagation, backward differentiation on a computation graph, is used to compute the gradients of the loss function for a network. Neural language models use a neural network as a probabilistic classifier to compute the probability of the next word given the previous n words. And neural language models can use pre-trained embeddings or can learn embeddings from scratch in the process of language modeling. So there's the 20-second version of what we spent 3 hours on. Subham says, why ReLU for all hidden layers but softmax from the final layer? So softmax gives you out sort of like one thing, and for your hidden layers, you don't want to have the weights 0 except for one of them is 1. It will, like, basically you'll have a bunch of weights or possibly neurons that never get activated, and then, I mean, why have them? So the neurons dying is a problem with vanilla ReLU, which is why people tend to use leaky ReLU. So instead of just like leaky ReLU, nope, leaky ReLU with a U on the end. There we go. It has like a little bit of a, here we go. So instead of being 0 for any negative value, there's a slight decrease. It's not 1-to-1 like it is for the positive values, but you never have, it's rare for you to have the weights in a cell being 0. Bubble Ride said something, but it's redacted. No worries. Chirag says, just wanted to know what model should I use for checking the compliance terms in calls made by call centers in medical domain, say HIPAA violations, etc. I will wait to the end. That's not a problem. Oh, yeah, that's a hard problem. I would not use deep learning for that. I would probably, I don't know, maybe I would. Yeah, hard problem. I'll stick that in my hat for the end. Remind me. So let's read the biographical and historical notes, because science is a social art and it's good to know who did things, and then maybe get to some implementations maybe. So the origins of neural networks lie in the 1940s McCulloch and Pitts, 1943. A simplified model of the human neuron as a kind of computing element that could be described in terms of propositional language. By the late 1950s and early 1960s, a number of labs, including Frank Rosenblatt at Cornell and Bernard Windrow at Stanford, developed research into neural networks. This phase saw the development of the perceptron, Rosenblatt 1958. and the transformation of a threshold into a bias, a notation we still use, Windrow and Hoff, 1960. The field of neural networks declined after it was shown that a single perceptron was unable to model functions as simple as XOR. Minsky and Papert, 1969. And this is something we talked about in, I think, section 1. While some small amount of work continued during the next 2 decades, the major revival for the field didn't come until the 1980s, when practical tools for building deeper networks like error backpropagation became widespread. Rumelhart et al., 1986. And this first bit where people just sort of ignored it for a while was known as the AI winter, or one of them. Bubble Ride says, how many outputs are usual in NLP? It depends on the task. If you're doing a binary classification task, then 1. If you are doing something like sequence to sequence modeling, so like machine translation, then that's, I mean, you get 1 output at a time, and then you sort of slide over both of the sequences. This is maybe a pretty deep topic to get into. It depends. It depends on your task. Kanishka says dimensions 50 to 300, usually 100 to 300 are used, I believe. Oh, never mind. You meant the output classes. Yeah, I mean, and dimensions will also depend on your particular task. And it's so frustrating. There's not really any way right now in the field to know a priori what the best structure for a network is going to be. And this is the thing that I find really frustrating about neural networks as a paradigm, is that we have empirical results. So we have evidence of some things working in some situations, but we don't have a lot of strong theoretical, framework around why that is. And as someone who is a scientist, it drives me nuts. Kanishka says it's all empirical. Yeah, basically. There was a paper at ICML this year that I loved, which showed that it showed with proofs that if your hidden layer isn't larger in dimensions than your input layer, you'll never be able to model a non-contiguous decision region, which I think is great. So if you have if your decision region that you need is like a circle, you don't have to have a net where the hidden layers are bigger than your input layers. But if it's something like polka dots, then you do need it. Kanishka says, what paper was that? Oof. I know I tweeted about it. Yeah, I'll repost that tweet. Element HTTP says, it works, but how? Yes, yes. And that to me is fairly frustrating. So I can't tell you what to do and why you should do it. I can tell you some things that some people have tried that have worked for them for their particular thing. But sort of figuring out what hyperparameters you need for your project is at this point still guess and test. Softmax is good at giving you probabilities for each class. This is Roshan Chudhari. Sorry if I get anybody's name wrong. That's 100% on me. Your names are beautiful, and it's me. I'm the bad one. Hence, ideally used for multi-class. Here it is therefore used for the output layer, so we get the probability values for each class. Correct me if I'm wrong. Nope, that's right. Bubble Ride says, I'm not a scientist, so I shruggy. Yeah, I like to know why, gosh darn it. That's why I stayed in school for so darn long, because I just want to know why things are the way they are. Yeah, which as a practitioner is just, it's frustrating. It's frustrating. You just got to try things until something works well enough for you. All right, back off my upset soapbox. While some small amount of work continued during the next 2 decades, so after the 60s, a major revival for the field didn't come until the 1980s when practical tools for building deeper networks like error backpropagation became widespread. Rumelhart et al., 1986. During the 1980s, a wide variety of neural network and related architectures were developed, particularly for applications in psychology and cognitive science. Rumelhart and McClelland, 1986b, McClelland and Ellman, 1986, Rumelhart and McClelland, 1986a, Ellman, 1990, for which the term connectionist or parallel distributed processing was often used. Feldman and Ballard, 1982, Smolensky, 1988. And the connectionist modeling in psychology is still very much an ongoing field, but it's diverged pretty radically from neural networks. Also, Paul Smolensky, fun fact, is Or at least he was. I don't know if he's still there. He was visiting at the University of Washington while I was there for a bit. Many of the principles and techniques developed in this period are foundational to modern work, including the ideas of distributed representations, Hinton, 1986, recurrent networks, Elman, 1990, and the use of tensors for compositionality, Smolensky, 1990. By the 1990s, larger neural networks began to be applied to many practical language processing tasks as well, like handwriting recognition, LeCun et al., 1989, LeCun et al., 1990, and this is where the MNIST dataset comes from. Knishka says, Smolensky is in the optimality theory guy. Yep. I am really pleased somebody's bringing up OT in the chat. High five on the internet. This is a linguistic theory for representing phonological transformations. Fab1 says, I am a social scientist by training. The lack of theory kind of drives me nuts too. Yes, I know. Handwriting recognition, MNIST. If y'all have dabbled before, you might have run into that. And speech recognition. Morgan and Bourlard? 1989, Morgan and Bourlard, 1990. By the early 2000s, improvements in computer hardware and advances in optimization and training techniques made it possible to train even larger and deeper networks, leading to the modern term deep learning. Henton et al., 2006, Bengio et al., 2007. Oh, hey, that's the paper somebody linked. I don't know if it's the exact same paper, but same author. We cover more related history in Chapter 9. Kanishka says, high five back. They won a Rumelhart Prize for OT. Oh, I didn't know that. Trog says, what do you think about handwriting generation? Shrug. I am just, as a person, less interested in image tasks. I know I should be more interested, and that's where the cool stuff is happening, and image processing is like 5 years ahead of NLP, and I know all that. But, I don't know, I think pictures are kind of boring. It's just me. Yeah. There are a number of excellent subjects on the book, excellent books on this subject. Goldberg, 2017, has a superb and comprehensive coverage of neural networks for natural language processing, and I think that's Yoav's book, and I have heard good things about that. For neural networks in general, see Goodfellow et al., 2016, and Nielsen, 2015. So, solid recommendations. And this is the end of the chapter, and now we can look at the citations. Actually, not that many citations. It is a young field. Well, okay, not that young. As we just found out, it's been around for a while, but really applying it to NLP in this way is sort of relatively recently. Kishka says, I have that book next to me right now, LOL. Yeah. Community of scholarship, y'all. We've got a shared background knowledge. I was going to say something, and I got excited. Oh, right. So the thing that was happening sort of behind the scenes here when people are like, why were we not using neural networks? What happened? We, the NLP community, was really into rule-based systems and expert systems. And a lot of chatbots are still rule-based and expert. That's one place where neural networks have had really weird outputs and sort of unpleasant, unintended behavioral consequences. So there's more work into neural chat generation, but that's really sort of the last stronghold / bastion of expert systems and hand-built rules at this point. Bubble Ride says, any recommendations for packages? Where do I find these dictionaries? So for the dictionaries, I'm assuming you're meaning embeddings, and we can look that up. So it is 9:48. We got about 12 minutes. I don't know if that's enough time, but let's look up embeddings. So this is the tags page, and a lot of things should be under the linguistics tag because I sort of seeded the tags, and I think linguistics is a good tag. So that's where we're doing. Fab1 says, when will neural networks create dank memes? I mean, when you build the meme generation bot. Yeah, I actually have a friend who does work on humor, but I think he's mostly using rule-based systems at this point. I don't know what Rick's up to. Let's see. Rick. Yeah, there we go. What have you been publishing, Rick? Are you still working in humor? 2015, 2018, word problems, language modeling. Oh, we co-authored a paper. Formal pragmatics, understand. Oh, okay. So it looks like maybe he hasn't been working on humor since like 2016. Yeah, good question. What was I doing? Oh, right. I was looking up embeddings. And I know I've uploaded a bunch. So for embeddings, I would recommend that you pick something that's going to work well with your specific task. There we go. So we've got Glove. I think we have several different instances of Glove. Glove is out of Stanford. Kishka says, my advisor did a bunch of humor research. He worked with Raskin, but this was the pre-memes era. I mean, I think memes are a rich vein, especially because they are images, and image work tends to be a little bit further ahead of NLP work. So we've also got, so the first one was Glove on Twitter. We've also got Glove from Wikipedia and GigaWord 5. I don't know, maybe that's what my next big project will be. Maybe I will finally touch image processing. Convolutions. No, that's not fair. Convolutions are used for language stuff too. There's a lot of people using them particularly in speech, because you can do a Fourier transform on a wave signal to create a spectrogram, which is basically a picture. Yeah. Ryan says, mixed of images in NLP, really. I feel like most people would probably just take the flat memes as input and would end up with, actually, you know what? This is how research happens. Generation deep learning. That would be probably what, CVPR? Are the CVPR papers out for this year yet? On memes and meta memes from 2009. Okay, so this is like the scholarly definition of meme. Predicting and generating popular meme descriptions. So this might be more like image labeling, and this was at NACL. Carnegie Mellon. Blah, 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 blah. Language of memes. Study the correlations among popular memes and their wordings and generate meme descriptions from raw images. So this is like halfway through. So they are using key point detection. Okay, so they are actually detecting meme templates that have been generated by a meme generator. So that's not quite the same question that you brought up. Fab1 says, I started something, sorry. No, this is interesting. Maybe this is going to be the thing that'll finally get me to touch image processing. Actually, okay, let's see who cited this, because that might be sort of other meme scholarship. I do know some people who study memes, but mostly from a conversational analyst stance. Understanding and predicting visual humor. Okay, that sounds promising. Witty wordplay in image description. It's an archive. Is there another version of it as well? Was it published anywhere? Okay, yeah. It was published at ACL, so that's probably relatively high quality work. Learning for connected. Oh, Wasserstein? I thought that said Wittgenstein, and I just glazed over. Deep brain learning, healing the heart. Extreme learning machines, deep learning method. All right, let's try this. Humor is an integrated. So this is We Are Humor Beings, Understanding and Predicting Visual Humor from CVPR 2016. So CVPR is more likely to have vision papers. In this work, we are interested in the question, what content in a scene causes it to be funny? As a first step towards understanding visual humor, we analyze the humor manifested in abstract scenes and design computational models for them. Abstract scenes are not quite memes. Necroduke says, just join the session, so I don't know what you've talked about, but I think I would maybe shout out computational humor. Kanishka says, it's been a thing for a long while. Yeah, we're specifically looking for meme generation with deep learning. And I think actually the place we might want to go to learn about this is GitHub. We might have like a student project that somebody's been working on. Oh, Twitch is down. Oh well. Looks like there was only one person watching, so. Can I, what? No, I just want to, there we go. I just want to search GitHub. I am not signed in right now. I've forgotten what the signed out place looked like. Check out Victor Raskin's work. Meme generation. Victor Raskin. Victor Raskin. Semantic Mechanisms of Humor. 2012. Ontological Semantics. Joke Similarity in a Joke Representation Model. Primer of Humor Research. Natural Language Watermarking. Watermarking natural language text by embedding small portions of the watermark bit string in the syntactic structure of a number of selected sequences in the text. Oh, that's kind of cool. That sounds more like security, though. Assurance and security. Empirical verification of a general theory of verbal humor from 93. Not for memes, though, for general humor. Fab1 says, I found this, which sounds interesting, but isn't about meme generation. Memorability map generation. You may not be able to post links. If you can just tell me what to Google and I'll find it. Code is question mark number of results. Oh, yeah, I think I can sign in. And do my authentication code. And I'm actually going to drag this into another window really quick because I learned my lesson last time. Like, I'm sure it would be fine. Y'all would still have to use my password, but. All right. Did I misspell meme? I did misspell meme. Let's see. Code. Deep AI meme generator. There we go. This sounds like exactly the thing that I'm interested in. Project for Stupid Hackathon, Madrid 2016. Okay, so this is a little bit vintage. Necroduke says dank learning paper. Printed popular memes. This is meaningless. Okay, yeah, the footnotes. Okay. So this is an unfinished hackathon project. The witty word play, I think, is building on the pun research. Let's see. Is there something actually useful? I mean, I wouldn't, like, if you're doing like research, I wouldn't necessarily recommend just sort of wandering around GitHub until you find something to copy and paste. It's not, you need to pay attention to licenses. Oh, here we go. Oh, this looks like a rejected paper, maybe. Let's see. Challenges in automatic meme generation using deep neural networks. Today's internet is full of memes, small chunks of data which represent a large proportion of a social network's communication protocol. Oh, this is memes in like the Dawkins sense, not visual memes. Oh, dank learning paper. If what I'm saying is out of scope, let me know. I'll be quiet. No, I'm always happy to hear about things. Let's try that. Hey! Generating memes using deep neural nets. That was the question that I had. I should have gone to archive. I don't know. Archive is a little, I don't always trust archive work. I won't say I've been burned because I haven't cited something that was later turned out to be like straight up garbage, but I have read straight up garbage on archive. Yeah, paper repositories are great, but I'm specifically thinking of, there's basically a phrenology paper that showed quote unquote, you could detect quote unquote criminality from pictures of people's faces. And now there's a startup that's trying to do the same thing. I am really unhappy, and hopefully they are removed from being able to do that. All right. Our model produces original memes and that cannot on the whole be differentiated from real ones. Oh, you forgot to use the backtick instead of the open quote there. All right. A meme. I just want to see the results. Okay. So they're taking an established format and captions and generating new captions for the given format. That makes a lot of sense. I was sort of thinking you'd do it just like you just feed in a bunch of image files and out they come. Yeah, Knisha says archive has a bunch of flag painting papers, mostly in the minority. Yeah, no, there's a bunch of... Yes. I also have feelings about chasing state-of-the-art as a way to do a field in general, but Fab says that is quite a claim. It is, isn't it? Set honesty to 95 and humor to 60%. Tara's Interstellar. Okay. Dude, I have no nose. I should start studying for finals. So this is averaging over the embedding, so just sort of saying the most likely word. And attention is an attention-based model. When did this come out? June 2018. So it's probably using some variation on transformers. Would be my guess. Not having actually read the paper, I'm just scrolling looking for memes. So scene images. Okay. Oh, these are generated on images it's seen and then images it hasn't seen. Yo dog, I heard you like memes, so I took an arrow to the knee. That's Kanisha says, I wish you were a student in my lab, lol. My advisor would have loved you. She likes theory more than state of the art. Your advisor is correct. That one says, they are memes, sure, but are they dank? I'm inclined to say no. The only one that I think follows templates well, I don't know. I think this one is kind of okay. Except it's a pulsar and not a dark hole. It's not a dark hole. It's not a black hole. This one might be okay in context. Kusha says any linguistics-based person would be like that anyway. Yeah. Fab says this is how I feel when I look at my teeth. Yeah, I don't like. There's no strong feeling there. It's a very neutral face. I feel like to be a good meme image, there should be a strong feeling in the face. There should be like a lot of expression. And it's just how I feel on it. This might be the author, or these might be the authors. Yeah. These look human generated by someone who doesn't know how memes work. This looks like a meme that like my mom would make. You know, like when somebody who's not really fluent in internet culture is like, oh, I've seen some like pictures with text on them, so I'm gonna put text on a picture. It does not seem fluent. Fab one says what? Yes, like the what face. That's a very good example of a very expressive face. Yeah, I don't know. No, maybe memes is the next thing. The face you make one is Richard Socher. Oh, that's good to know. I don't know who that is, but I'm gonna look it up. Whoop. Natural language decathlon. Chief scientist at Salesforce. Previously adjunct professor at Stanford's computer science department. And founder, CEO, CTO of MetaMind, which was acquired by Salesforce in 2016. All right. Fab1 says, so we created mom memes. Yeah. Yep. They're not good memes, let me put it that way. All right, so it is a little bit after 10, and I do have a lot of work to do today, so I should wrap this up. But thanks for joining me today. We finished the chapter. We did not do any implementation, but we did learn about meme generation. So that was definitely interesting. And because we haven't talked about attention, because we've talked about embeddings, the glove average is probably comprehensible at this point. You learning? If you didn't know about it ahead of time. Yeah, I think the next paper I want to read is probably the All You Need Is Attention paper. I don't know, but we'll see. We'll see how I feel next week. Bubble Ride says, the generated memes lack having a joke. Yeah, they're not funny. And Duke says, this was fun, even if I joined in the last 10 minutes. Well, the first 50 were math, so depending on your feelings to math. And Fab1 says, sorry if I crashed the planned implementation with my meme question. It's fine. I'm always less good at coding in the morning anyway. I tend to be good at like reading in the morning, and then I sort of push my technical work a little bit further into the afternoon. So thanks for joining. I'm gonna call it a day here and do my other work that is not chatting with people and looking at memes. And I will talk to you guys on Friday probably. I'm planning on streaming on Friday, but we'll see how I feel after Thanksgiving. Alexander says, please, attention. All right. Attention is good. And Necroduke says, I'll definitely rewatch. Math is something that always needs resharpening. Oh, don't I know it, man. It goes dull very quick. All right. And see you guys on Friday. Maybe. Bye-bye.